So you've got a computer to highlight something in an image. Awesome. But the result is, well, a total mess. How do you turn that noisy, raw computer-generated mask into something clean, precise, and actually usable? Today, we're diving into exactly that, a fundamental skill in medical imaging. Let's get into it. And just to give you a little motivation, this is where we're going. Look at that. A perfectly clean, beautifully accurate mask of the lungs laid right over the original X-ray. This is the goal, the finish line. This is the kind of image you can actually use for analysis. It's clean, it's clear, and it's exactly what we're going to build. But of course, we don't start there. Nope. We start here. On the left, you've got the original chest X-ray. And on the right, that's the raw output from a basic computer algorithm. You can see it's noisy, it's got holes in it, and there are all these extra little blobs that are definitely not part of the lungs. Our job is to get from this digital mess to that masterpiece we just saw. And here's how we're going to do it. First, we'll talk about why these masks are so messy in the first place. Then, I'll introduce you to our 4 essential cleanup tools. After that, we'll build our own cleanup pipeline, step by step. We'll even learn how to fine-tune it for perfect results. And finally, we'll talk about why this classic technique is still so incredibly important today. Okay, so let's start at the beginning. The messy mask problem. Why do we even have to do all this cleaning? Well, the simple truth is that computers are rarely perfect on the first pass. Whether you're using a simple, classic technique or even a super fancy deep learning model, that initial result is almost always going to be a little bit messy. You get these little salt and pepper specks, random holes inside the object you care about, and rough, jagged edges. This isn't a failure, it's just a totally normal part of the process that always needs a dedicated cleanup stage. So, to do that cleanup, we need the right set of tools. In the world of computer vision, these tools are called morphological operations. Now, that sounds super complicated, I know, but trust me, they're actually really intuitive ways to reshape and refine our messy mask. Now, before we get to the tools themselves, we have to understand the one thing they all have in common, something called a structuring element, or a kernel. Just think of it like a tiny magnifying glass, maybe a 5x5 grid of pixels, that we slide over our entire image. At every single spot, it looks at a pixel and its neighbors and decides if that pixel should be white or black. The size and shape of this little kernel is what controls the power of all our cleanup operations. All right, so here are our 4 main tools. First up is erosion. It literally shrinks the white areas, which is perfect for making tiny noise blobs just disappear. Dilation is the exact opposite. It makes the white areas grow, which is great for connecting parts of the lung that might have gotten broken apart. But then you get the really cool combos. Opening is just erosion, then dilation. It's fantastic for removing noise without messing with the size of the main object. And closing, that's dilation, then erosion, is your absolute go-to for filling in those annoying little holes inside an organ. And here's what that actually looks like in practice. On the far left, that's our noisy raw mask. See what happens with erosion? Everything just shrinks down. Dilation? Everything gets bigger and puffier. But check out opening. The little specks of noise are gone, but the lungs look about the same size. And with closing, you can see those holes inside the lungs starting to get plugged up. It's pretty cool to see it in action. Okay, so we've met our tools. Now it's time to be a little strategic and put them together in just the right order to build our complete lung extraction pipeline. Our pipeline is going to have 4 simple stages. We'll start with that raw, messy mask. Then we apply an opening operation to get rid of all that small salt and pepper noise. Next, we use a closing operation to fill in the holes. And for the grand finale, we just tell the computer to keep the 2 biggest white blobs in the whole image, which, hopefully, will be the left and right lungs. So step 1, we start right here. This is our raw, chaotic mask, with noise just splattered all over the place. Now for our first move, a morphological opening, and just watch, poof, the vast majority of those tiny disconnected white blobs just vanish. It does a great job cleaning up the background, but notice we still have some of those pesky holes inside the lungs themselves. And that's exactly where closing comes to the rescue. It marches in and fills those internal gaps, making the lung regions solid and whole. You have to do this to get an accurate shape of the organ. And now for the final elegant touch. We literally just tell the algorithm, find all the separate white blobs, measure how big they are, and throw everything away except for the 2 biggest ones. And just like that, everything else disappears, and we are left with 2 perfectly isolated lung fields. And there you have it, the full journey, from a complex X-ray on the left to a clean, analysis-ready mask on the right that perfectly zeroes in on what we care about.
This transformation right here is the entire point of our pipeline.
But, just building the pipeline is really only half the battle. To really master this kind of thing, you have to know how to tune your tools. Which brings us to a really, really important question. We talked about that little sliding window, the kernel. Does the size of that thing, does it really make a difference?
Oh yeah, it makes a dramatic difference. Just look at this. This shows the final result of our whole pipeline, but run with 4 different kernel sizes. You've got a tiny 3x3 kernel on the left and a huge 25x25 on the right. You can think of the kernel size as the strength knob on our cleaning machine. So let's break that down. A kernel that's too small, like the 3x3, it's just not strong enough. See how it leaves a bunch of noise behind? But one that's way too big, like the 25x25, is total overkill. It smooths everything out so much that it actually starts to merge things that shouldn't be merged. The sweet spot, at least for this particular image, is that 7x7 kernel. It's got the perfect balance of being aggressive enough to clean the noise, but gentle enough to preserve the important details.
Okay, so we've built our pipeline, we've tuned it, but you might be wondering, with all the crazy AI and deep learning stuff out there today, why are we even talking about this classic technique? Does it still matter? It absolutely does, because what you've just learned isn't some dusty, old academic exercise. This exact process, going from a raw image to thresholding it, cleaning it with these operations, and isolating the components, this is a foundational pipeline in computer-aided detection. It's logical, you can explain every step, and it just works. And hey, don't just take my word for it. This is the exact pipeline that powered the very first computer-aided detection systems, or CAD systems, for screening chest x-rays. And what's incredible is that variations of this are still deployed in real clinical tools that doctors use today. That just shows you how powerful and reliable these fundamental ideas really are. And that brings us to a final thought. This classical step-by-step method is powerful because it's reliable and it's based on clear rules about shape and size. But that leads to a fascinating question to leave you with. What subtle patterns, what hidden textures that might indicate disease could a method like this miss that a modern AI trained on millions of examples could learn to see?